Example 2. We'd like to solve cosine of 2x is equal to cosine of 1x over the interval 0 to 2 pi. Anyone? Any ideas?
You have to read the cosine.
Isolate one of them.
All right. Well, here's the thing. They're both cosines, which is nice, right? Yes. So we should be able to move it over and solve for it.
Yeah.
But if I do that, what is cosine of 2x minus cosine of 1x?
Cosine of x.
Does it work that way? Can you subtract angles? No. What was the very first rule we said when we started this section? We said if the two angles are different, you first have to use an identity to make them the same angle. So because we're dealing with a 2x here and a 1x here, we can't go any further until we have those either both 2x or both 1x. So we're going to have to reach back and we're going to have to think about what we know about the double angles. So if we talk about cosine of 2x, we know that it equals cosine squared of 1x minus sine squared of 1x. Agree? So that's one possibility. We also know that it equals 2 cosine squared of x minus 1, or that it equals 1 minus 2 sine squared of x. So we could choose any one of those three things, and we could replace cosine of 2x with it, and then they would all have angles of x.
I like this middle one.
Why do you like the middle one?
Because there's no sign.
There's no sign. I think that's a good idea because what we have up here would all be cosines, right? So let's try that one. Let's substitute on the left side, instead of cosine of 2x, 2 cosine squared of x minus 1. Perfect. Now they're all cosines and they're all plain x's. So we can get it equal to 0 and see what's happening. So we have 2 cosine squared of x minus cosine of x minus 1 equals 0. And I think that factors. It's a quadratic, and so I think you can factor it. Let's try it. In order to get 2 cosine squared, one of my first terms needs to be 2 cosine and the other needs to be 1 cosine. Is that right, you guys? To get 2 cosine squared? And then the only way to get negative 1 is to put a positive 1 and a negative 1 here and here. We just have to be careful about which, so I'm just going to plug in and figure it out. This one's 1, this one's 1, and I want the larger one to be negative, so that would make this guy negative and this guy positive. I know some of you do bottoms up or tic-tac-toe, I don't know. Whatever it takes. I just do trial and error where I just pick it apart and figure it out. Whatever it takes to get it factored. If you have to, go off to the side and do it this way. So like 2a squared minus a minus 1. Factor that and then put the cosines back. But get it factored. Any questions about where we are? No? Now what do I do? Set both of them equal to 0. So we'll take the first one, 2 cosine of x plus 1 equals 0. And we'll also set cosine of x minus 1 equal to 0. And we will solve both of those like they're 2 separate problems, and we will isolate the cosines.
Are you sure that's right?
No? Yeah, I'm sure. I think it works.
Like if you multiply 1 times cosine of x, isn't it positive cosine?
Yes, but this one's negative 2. And a negative 2 and a positive 1 here make negative 1. If you redistribute it. Yeah. I think it's right. Did anybody else check it? Yes? We're good? Okay. So over here, we're going to isolate the cosine. So I'm going to subtract 1 and divide by 2. So it looks like cosine of x has to equal negative 1/2. The good thing is that when we use that double angle identity, our coefficient became what? 1. So we don't have to worry about multiple revolutions and dividing by coefficients. All we have to do is just solve it just like we did from section 6.2. So we need a reference angle, which in this case is, where's cosine 1/2? 60 degrees?
Yes.
So that would be pi over 3. But it's negative, so I have to move it into quadrant. Anybody? Where's cosine negative?
3,
2
2, and 3.
and 3, yeah. So if I want to move pi over 3 into quadrant 2, I say pi minus pi over 3 is 2 pi over 3. So there's the quadrant 2 answer. And then if I want to move it into quadrant 3, I have to go pi plus the reference angle, so pi plus pi over 3. So that would be 4 pi over 3. And a lot of you know your unit circle well enough you don't have to worry about that. You just know which ones have, what coefficients in which quadrants. Okay, so there are our first two answers. Then we'll come over here and we'll talk about this side. Cosine of plane x is 1. That only happens once. Where?
45.
Cosine, not tangent.
Yeah.
Where's cosine 1? Is it at 0 or is it at pi over 2? Cosine is 1 at 0. So technically, I guess it could happen twice. It could happen at 0 and at 2 pi, right?
But you
So
can't use
we can't use 2 pi, yeah, I think you're right. Because 2 pi has a parenthesis here. So I can only use the one with the bracket if I get those two. So we can use 0 and not 2 pi. So it looks like those are our three answers. And of course you can plug back into the original and check it. Your book will put them like this. 0, 2 pi over 3, 4 pi over 3 in braces. And they all three do check out, you guys. Questions about that? Pause for a second. Okay, just real quick, as a caution, think back to that example. Because 2 is not a factor of cosine of 2x, you can't just divide that by 2 and make it equal cosine of x. The only way to change cosine of 2x to a trig function of just x is to use one of the double angle identities. So be really careful with that. You can't change angles just by dividing them out in the beginning of a problem, okay? So a lot of mistakes are made there. Just like we were talking about, could you subtract them and change the angle? The answer is no. The only way to change an angle during the process is to use an identity. Let's look at a new example. We would now like to solve 4 sine of theta cosine of theta equals square root of 3 over the interval from 0 to 360 degrees. So we're back to degrees, so that's nice. And I want you guys to kind of like really put a star by this one, because this is one of the ones that I think people have trouble seeing on their own. As it stands right now, how many trig functions do I have? 2. Okay. If I get it equal to 0, however, can I factor anything out? If I say minus square root of 3, is there anything I could factor out of that? If I had 4 sine of theta cosine of theta minus the square root of 3 equals 0. If I did that, could I factor anything? No. Okay, so that doesn't work. There's 2 of them, so I can't isolate them. I can't separate them by factoring. I can't use the quadratic formula. And that makes me think that I'm down to that last option that says you can use an identity, okay, to rewrite it in a form where there will be a single trig function, or you can square both sides and then use an identity. And we could square this, you guys. We could square both sides of that, okay, and then we could replace one of the signs, either the sine squared or the cosine squared, with the Pythagorean identity and go from there and get them all to sines or all to cosines. Make sense? We could do that. However, there is an easier way to do this. And a lot of people don't see it, so a lot of people will go that long way, but I do want to show you the shortcut. For this particular problem, do you see how it's 4 sine of theta cosine of theta? Okay. If I factor that 4 from the very original right here, 2 times 2 sine of theta cosine of theta equals square root of 3. Do you see this much of it right here is exactly the double angle identity for sine? So I could take all of this and replace it with sine of 2 theta and take it from 2 trig functions into 1 trig function. Now it gives me a different angle, but that's okay. We can deal with the angle at the end. Now that we're there, it's a single trig function of a single angle. Well, technically of a double angle, but still. So if I were going to solve it from there, I would just do what? Divide by 2 and isolate the sine of 2 theta. Okay, and then forget about the 2 theta for just a minute and just find me a reference angle. Where's sine square root of 3 over 2? 60 degrees, right? So that's a 60-degree reference angle. So that means that in one revolution, that's going to occur in quadrant 1 and 2. So I know that 2 theta, the angle here, has to equal the quadrant 1, which is 60, and the quadrant 2, which is 180 minus 60, which is 120. Those are the only 2 places that sine of 2 theta is going to equal square root of 3 over 2. When 2 theta is 60 or 2 theta is 120. Now we have to solve it for theta. Now that we've gotten rid of the sine, we've done the inverse sine, we found the angles. Divide both sides by 2. Oh, I did something wrong. What did I forget, you guys?
You got
This is 1 revolution. We're skipping a step.
The 2.
Ooh, yeah. I'm supposed to generate how many revolutions if my angle is not 1 or 1 theta? 2, yeah. This is only 1 revolution. So this is quadrant 1, quadrant 2 for 1 revolution.
420.
I'm really bad about that. I will a lot of times lose the last 2 for that reason. So try to make a note of that because I get in a hurry and do it, and I know you will too. So what we do is we just add another revolution to it. So you add 360 to generate 2 more answers that are beyond 360. So if we add 360 to this one, I'm at 420. And if I add 360 to this one, I'm at 480. And those are called your second revolutions. And that's all I need. If I needed 3, if this were a 3 right here, I would add 360 to both of those and get 2 more answers. Now we can divide all 4 of those by 2 to isolate the theta. So we have theta equals 60 over 2 is 30. 120 over 2 is 60. 420 divided by 2 is 210. And 480 divided by 2 is 240. Notice that every one of those is back in the required interval. So if you generate off and then divide out the coefficient, it will put them back where they need to be. And then you can check them back into the original, and all 4 of those should work. There's no reason they shouldn't unless we made a mistake. You'll only get extraneous solutions if you do what during the problem? Square both sides.
Yeah.
Remember that? And we didn't square both sides. We used an identity, but we didn't square both sides. So all 4 of these will work. So I'll break here. You guys check them, and then you can take a break. Split it up. Some of you guys check the first one, some the second one. Each row check 1. Check 30, 60, 210, 240. Back into the original right now. Okay, so we checked those and we decided all 4 of them work. All right, you ready? Okay, the next little piece of this is the same problem, except it says to generate for all solutions. Well, we've already generated for 1 revolution, so tell me those. They are 30, 60, 120, not 120, was it 210? 210, yeah, 210.
And then 240.
And 240, okay, 210, 240. Okay, those were for 1 revolution. Now I need to generate the new ones, okay? What's the period of the original?
2 pi.
2 pi over b, so 2 pi, which would be, in degrees, that would be 360. So if I add 360 in to each of these, that should generate all of my solutions, correct? So add the period times n. Does anybody have their book out? Anyone? It's okay, we can pause and look it up.
You're going to show how dumb the book is.
No. So we looked in our book and they listed only these 2 answers. So we had a couple of questions there. Where did these 2 go? And why are they adding 180 rather than 360? Okay? It's a little bit hard to explain, but I can tell you where the 180 came from. If we back up right here, we didn't actually solve it with thetas. We solved it with 2 thetas. Does that make sense? Yes? Okay, we solved it with 2 theta. Well, the period of 2 theta is not 2 pi or 360. It's 2 pi over 2, which is 1 pi, which is 180. So technically, we should be able to do this by adding just 180 to them. So you're supposed to use the period from what you actually solved for, not the original. Does that make sense? That's where their 180 came from. Does anybody know where these went?
It's 30.
There's
plus
1080s
180
in there,
and-
but
Technically, they're there. It's a redundancy. Does that make sense? Okay, so it is a redundancy. Now, either one of these things is not wrong. Like, it's still going to get them all, okay? But if you list it this way, you have to list all 4. But if you list it this way, I think you have to list all 4 for that one. If you list it this way, add 180 to this guy. What do you get? This is a redundancy of this one. So if you bring it down to 180, if you use, the period of what you actually solved, it brings it down, and that one's redundant. Add 180 to this one. 240. That doesn't happen if you leave this 360. You don't get those redundancies. Does that make sense? Like if I add 360 to this, I'm at 390. I'm not in quite the same place. And you can generate all of them from either these 4 or these. And your book is always going to give you the shortest. What a lot of my students do, they'll catch the 180. They'll say, oh, well, I solved it for 2 theta, not for 1 theta. And they'll catch that and they'll do the 180, but they will leave all 4. And that's okay too. But just understand the book is going to write it in the simplest way possible. So if you don't understand where the other 2 went or how it changed from like you think it should be 360 and they have a 180, it's probably something that went on during the solving and they're realizing there's an easier way to write that or a shorter way to write that. Does that make sense? But the main goal is to generate all the answers. So technically, either one of these would be sufficient. Is that okay?